And our next speaker will talk about some of the precision management, maybe some more implementation, what some opportunities we have as far as managing our farms. So Dr. Isabella Condotta has received her PhD in biological systems engineering from University of Sao Paulo, ESOLC in Brazil, followed by a postdoc at University of Nebraska-Lincoln. She is currently an assistant professor in the Department of Animal Science at the University of Illinois. Dr. Condotta reduces animal stress, improves animal well-being and environmental sustainability, and helps farmers make better and more efficient management decisions by developing precision management systems for animals. Her interdisciplinary research applies advanced technologies such as image and audio processing and machine learning algorithms to acquire and analyze individual animals' electronic data, allowing continuous and automatic monitoring of their physical condition, behavior, health, and well-being. Please join me in welcoming Isabella.
Thank you all for being here. I think this presentation will tie nicely with the previous presentation. I'll talk about precision tools on the research side of things and how we think about doing research moving forward with the technology, but at the same time being applicable today and not only in the future. So let's start talking about the problem we are trying to address. Our world population is obviously increasing, and with that increasing in people, we'll have an increasing demand for animal products. At the same time, we can see some trends on labor availability at the farm. We see that there was a sharp decrease on labor availability over the past few years. Lately, the labor is maintaining somewhat constant, and you'll see the past few years, specifically for the livestock sector, we had a little bit of an increase. And then over the past 10 years, this labor availability is pretty constant. At the same time, we see a little bit of a shift on what our farms look like. We have increased amount of heads per farm and decreased number of farms. So we have more larger operations, and that means that we'll have more animals that a crew needs to take care of. And that brings a challenge, right? We need to increase efficiency on our operations. Not only increase efficiency, but we have to do that while still maintaining animal health, improving animal welfare, improving environmental sustainability, helping farmers making better and faster decisions, and also still keeping the system profitable. We'll see that use of technology can address some of those challenges. Here's a graph showing labor needs to produce 100 pounds of gain. And you will see that the labor needs have reduced over the years. That not only people have become more efficient on their jobs, but also technology has been helping with this efficiency. So what is precision livestock farming or precision management of animals? I brought here a formal definition of the management of individual animals by continuous, automated, and real-time monitoring of health, welfare, production, reproduction, and environmental impact. The big word here is real-time. We need to be able to know what's happening today at the farm and not what happened yesterday. And we need to be able to use that information in real time as well. How can we do that? This is a schematics. I'll show some arrows there. Will start making sense. A schematics of how precision management of animals systems should look like and where research can happen. We have a process there, our pig. And this pig is inserted in a microenvironment. We generally have good information about the environment that our animals are inserted. So we have information about the feed you're providing to your animals. You might have information about the climate, temperature, humidity, etc. You might also have information from your animal health history. You might have information at least on age, sex. And with that, you know what the response of those animals to their environments will look like by using sensors. The sensors, along with the information that you have from your environment and your animals, will provide inputs to algorithms. These algorithms will then output decisions that need to be taken at the farm. And this decision then can be sent to a controller. This controller can either be the farmer, who will take manual actions into the system, or for another automated controller that will take actions in a more automatic form. If you know what you expect from your system, such as how much an animal is gaining of weight, or how much they are feeding, or what the temperature in the environment should look like, you are able to make changes on that environment. Maybe provide a different diet to an animal, or take care of the animal in a health perspective, give antibiotics, or change pens or something that you need to do, and then that information can be used as a feedback and understand if your changes had a positive impact or not. Now here I brought a few examples of how we develop tools in this area. First of all, research on this area, it's always a fine line between what can be applicable today and what the scenario will look into the future. So you'll see that some of these applications, they are still pretty much being developed, and some can actually be applied today, and there are some commercial solutions already available. So let's take a look on this part. You cannot manage what you can't measure. That means that you have to be able to measure your animals in real time before you have any management decisions taken. The challenge here for precision technologies is how to monitor the animal's conditions in a fast, efficient, continuous, and non-invasive way. The non-invasive piece here is trying to address the welfare point of view. So the solution with technology would be transform some subjective methods of measurement into more objective methods of measurement that you can use sensors to take, and then obtain objective variables from that, and then use that to make decisions. Going back again to the schematics that I had, one thing that you need is information on your animals and their response to their environment. The way we collect animal response to their environments is using sensors. Those sensors could be either wearables or non-wearables. Here I brought a few of the sensors that I've been using, but keep in mind there are other sensors that exist, especially the electronic feeders, pressure mats, and different things like that. I brought cameras and microphones as our non-wearable sensors. That's more my area of research, and I brought some examples on this area. There are three main kinds of cameras when we are developing computer vision systems for animal management. A thermal camera that can provide you with thermal images, and those thermal images, they will provide temperatures on the surface, either on the animal or on the environment that you have. And that can provide information about if there is an inflammation on the surface of the skin, under the skin of the animal. It can provide information related to maybe onset of estrus. Then you have your RGBD camera. Those cameras, they are also known as either depth cameras or 3D cameras. They provide a 3D view of the environment. And these cameras are being widely spread now for uses that need the body dimensions, such as predicting animal body weight, predicting animal body condition score, and I'll show an example of use of those cameras in just a second for those two scenarios. And then there is your common surveillance camera, and that can provide you with either a color image or a night vision image, and it also provides a grayscale image. Those cameras, they survive better in the farm environment. They are better encased for those environments, but they have the limitation that they don't provide a third dimension. It's more a 2D image that you have available. And the microphones, ear tags first. Ear tags are your normal wearable sensor that if you have any sensor, probably you start with an ear tag. Can provide information, the ID of the animals, but depending on the ear tag, you can have activity. Some ear tags will have temperature on the animals and some sort of monitoring according to the behavior of the animal. And the microphones provides sound, and there are some analysis that you can make on those sounds to detect cough, for example, or you can detect a fight, or you can detect any vocalization of interest. So let's take a look on animal body weight and how we can use computer vision for animal body weight. I'll start with some research that I've published already. This specific research, I started in 2015, so 9 years ago, and now you can see some commercial applications using this type of technology. Just a general understanding of how this technology works, what it's actually doing. So this was a project that we used a depth camera or a 3D camera to produce this shape. This is the result of a top view image taken above a scale. And what you see there is just the body of a pig without the head. So the head should be on this side here. And that is the back side of the animal. So this is the back of the animal. And you generate a projected volume. If you only have a top view image, you can't really see what's happening on the sides. But this projected volume correlates well with animal body weight, as you can see here on this graph. Eventually, we improved on those models using artificial intelligence to both make the image processing step faster, but also make a little better predictions than just using a linear regression. But just by using a linear regression, you can see that you have good results. What an implementation looks like of something like this. First of all, an advantage of using depth cameras is that you can know how far you are from your ground, so you don't have to set a specific positioning for your camera to be at. So you could potentially at different farms position this camera in different places. It's just a matter of setting that beforehand. Now this is an animal taking a drink. So here we have a total of 4 drinkers. And then you can see is a top view. This is just the color image of animals coming to the drinker. This is a research that was performed in Nebraska. I'll show this video in just a second, but just so you understand what's happening, this is the depth view of that previous image. It's the same camera, just a 3D view. It looks like a grayscale image, but you see the pigs coming to the drinkers. These drinkers, they do have an RFID antenna in the panel, on the panels around the drinker, and the animals that have the ear tags that can be read. So on the right side, you'll see ID. The left side, you'll see weight. And you can see when the animal comes to a drinker, you get a weight, and then you get an ID. It's just an example of how this can be implemented at the farm. Now, body condition score. Again, our problem is usually body condition is done visually, right? You look at your, in this case, house, and you evaluate how is the condition of the animal. If they are overweight, they would get a score closer to the 5. If they are underweight, they get a score closer to 1. But this is a time-consuming problem. Not necessarily you're going to be doing this every day with every sow that you have. So how to automate this process? This is researchers published this caliper here to use as a way of at least not automate, but at least always get the same value instead of being a subjective measurement that's dependent on your opinion. We use that as our standard just to get that measurement always the same. And we also use ultrasound on the sows to get body fat information. After that, you can see us using this caliper on animals that were individually housed. These animals were just back from the farrowing barn. So you can see a very quick process. And I was shouting the numbers to a person that was putting down the numbers. It's still very manual, but quite easy to perform. Now, this is using the same caliper on group housed animals. This was our nice animal. She was probably one of 100 that actually cooperated, but most of the animals look more like this, right? So that's the reality of trying to develop solutions. It's not one solution fits all. If you have individually housed animals and you're only going to do body condition score at that moment, that's easy. But if you want body condition on group housed animals, how do you go about doing that? And we thought, well, maybe cameras would be a potential solution. That's what we did. Here again, animals were walking on a corridor on the left-hand side there. It's the depth image. You can see the pig here post-processing that image and then take off the head of the animal just for better results and then get that shape again. And this shape, what we did was just collect information on the rib region of the animal that we would use with the caliper, but now we are trying to get that information with the depth camera and getting that curvature information. And besides that, we got different measurements on the body of the animal, ellipse, perimeter of the body, and some other things, all with that depth camera. This is automated process to get dimensions on the body of the animal and correlate that back to body condition score. We didn't get perfect results, but we did get good results and an indication that maybe more research needs to be done on the sense of instead of correlating back to what we were getting on that caliper, correlating back more with the back fat, or just developing a new body condition system based on cameras, because obviously there were flaws with our caliper method, especially for the animals that we measure on the group house. But we were with a mean average error of 1 out of 22 possible levels on the caliper. So 1 out of 22, I don't think it's a bad error, but there's definitely room for improvement. Now, gait analysis is another area that we can use depth cameras to get some information. Here is where the animals were walking. There was a camera mounted on the ceiling. This is the view, color camera, and depth camera. It's actually the same camera that provides 2 streams. The animals just walked under that camera. If they were running, we walked them again. If they stopped, we walked them again. They were pregnant sows in this case. And then again, data analysis looked pretty much similar to the body condition score analysis that I showed, but now we were looking for 5 different areas on the animal: the head, and then left and right side of the shoulder region, and the hip region. And you'll see a video of what a non-lame animal looked like. We are plotting height of those regions against the distance where they walked. You will see this is a non-lame animal. And you'll see on this first graph, that's the shoulder of the animal. So one left shoulder is up, the right is down, and vice versa. So those are the 3 steps that the animal took. And you'll see the hip region doing the same thing. So you'll see that up and down motion that the camera can pick up. Now, when we had a lame animal, for example, I think you can see on that video, the animal is slower, stops more, and you can see a limp. And the head kind of bobs too. I don't have the graph of the head there, but I do have a graph of the shoulder first. You will see that motion of up and down completely disappears on the shoulder of the animal. But then on the hip, you still see that up and down motion. It's just the animal took more steps and took longer to walk the same distance. So that information then we use to train our, in this case, we used artificial intelligence models, neural networks, to predict. And we were getting an accuracy of 90% on lame versus not lame. But then when we had levels of lameness, things start getting a little bit worse on the accuracy. But if we could at least detect the animals that have problems and then send somebody to check on those specific animals, that's improving labor efficiency. Now let's take a look on behavior. This is more my ongoing research now. Those previous research that I just showed, they are published already. And this is what we can do if we can collect behavior automatically, in this case using cameras. Estrus detections, focusing on guilts, that's a complicated matter to detect because you obviously, for us to create a good data set, we need to first use PG600 to synchronize all the animals. And then what we were trying to do is automate behavior analysis, but also develop behavioral time budgets surrounding estrus to know if the animals actually went into estrus. We were both doing back pressure tests, but also doing ultrasound on those animals, trying to look for follicles. That sounded like a plan that was easy to accomplish, but it's proven to be quite challenging, especially because oftentimes we'll have a group of animals and several of them will develop cystic ovaries, so you really don't know when estrus actually happen. So we have some issues there, but we did get good initial results, and we're still improving on those models. So here's a posture recognition model. I don't think you can read, but those little yellow boxes, they are just showing if the animal is sitting, standing, kneeling, or lying down. We are very good with sitting, standing, and lying. We're not very good at detecting if the animal is kneeling. Generally, kneeling gets confused by this model with standing up. But using these models, we are developing this type of time budget. This is just an average of 6 animals. It's not a very large data set yet. We're still analyzing some of those things. But we are starting to see some patterns of lying down, standing up. This is day 0, which we're calling estrus day, and then 1 day before, 2 days before, 1 day after, 2 days after. We are going to increase that window, and we are looking for other types of behaviors as well. Now, moving forward, we are trying to see if we can detect some of those behaviors when animals are group housed. And the types of behaviors and postures that you would be looking for, they will change, obviously. If the animal is group housed, then you have some social behaviors that we should be looking for, such as mounting behavior. And those are the things that we're starting to look for to improve this kind of model. Now, motherability is another variable that we're looking for, specifically when it relates to crushing piglets. Here we are trying to detect information on both the mother and the piglets that would be able to give us just a general overview of what was happening at that pen when the mother crushed their piglets, and comparing mothers that crush more versus the ones that crush less. The final goal is to truly isolate all the variables that could cause crushing, such as health status of the animal, the crate design, maybe piglets that were sick or not. After all of that, is there still a motherability component to it that's more related to personality of the animal? And does that change over time with parities? Does a mother that's good mother on parity 1, do they become worse or better over time? Or they are always the same? So here's just our models being able to segment animals from the images, and we are looking for activity level, and we are trying to achieve individual piglet level, but when you have several piglets, that gets trickier. Here is one example of after you find the animals, you have to actually understand what they are doing. This is an example of output of classifying what the animal is doing. So lying on the left side there, and then standing. You can see there's some of those frames they are missed. This was the first iteration of this model. We are a little bit better than this now. But you can see that we are focusing on the cell here. Now, the next steps are not only understanding postures, but also behavior. We're looking for nursing behavior. So here at the top 5, we have several classes. Those are what the model considers the top 5 classes, meaning the animal should be doing one of those 5 things, and the top class is what the computer is guessing that the animal is doing. We're still improving on that, but we have classes that relate to both posture of the animal, and then behaviors such as eating, drinking, nursing the piglets, et cetera, et cetera. So we are trying to understand truly what the sow does to tend to those animals and understand if there are any characteristics that are related to personality. Now, feeding behavior and performance, this is the first iteration of this model. We got about 97% accuracy on predicting feed intake of the pen when just detecting time spent by at least one piglet at the feeder. So we just added all that time that at least one piglet was at the feeder, compared that with feed intake of the pen, and we got very good prediction. And this is the next step of this research, which is we have a tracking ID. I don't know if you can see, but there is ID 1, 2, 3, 4. And then the animals, when they are at the feeder, at the drinker, just standing. And I don't think this video has this example, but if they are lying down, sitting, and playing as well, we have some other behaviors that we're looking for. So all of that is very exciting, but what are the limitations, right? First thing, when we are developing research in this area, we have to consider that any living organism can be considered CITD, and I'm not the one that said that. Dr. Berkmans is the one that said that. So they are complex, individually different, time-varying, and dynamic. What does that mean when developing precision technologies? Let's take a look on the living organism aspect. This is an expectation of what a pig will look like inside a weighing scale in this case. And if we develop a computer vision system that will be looking for an animal that's getting in a scale from left to right and staying there a few seconds, we develop a computer algorithm to look for that. But pigs, they are not fun, right? They generally will do something like this, and our computer program is crashing now because it couldn't see a pig, but it should be seeing a pig. So we have some personality issues with pigs. They also are very curious, so if you try to put any sensor on their level, they will probably be chewing on that. So application needs to be taken in consideration. I think everybody relates to pigs being pigs. Another part is environment. If we're working with computer vision specifically, and now with depth cameras, if you are working with colors, you will see, if I tell the computer a pig is pink like this, and I have an environment that has a shadow on the pig, now half of the pig is actually gray, and half of the pig is pink. And you will see that on top of that, this pig is covered in manure. This brown here is not a coat pattern, it's just the animal is dirt. So am I considering those things on my model when I'm developing those? And that's actually when we go to the implementation step, things that companies and whoever is implementing this should be taking in consideration, not just test on those images that you took first, but actually trying those things out before going about selling a product. Another thing is, if we want to do precision, we really want to get to the point where we can do individual level monitoring. So this is an example of pig body weight in different genetics, right? So this was a study that we collected back in 2017. So you can see that animals are growing faster. We need to keep track of how fast my genetic line that I'm using is growing. That's good, but that's just average, right? If we look into an individual level, this is one animal when you weigh them every week. So that's what the curve looks like. Is similar, but if I was to compare a specific day here and here, you would obviously have variation. So if we're looking for a daily understanding of what was happening with this animal, you can see some up and down pattern. If this animal was sick, you would probably catch something here before you could see sick symptoms, or maybe at the same time, but you were not actually observing close enough. So if you can get daily variation, not only body weight, but any measurement that you were using to understand the health status of your animal, daily information is always better, but not necessarily easy to apply. One big thing is, if you want individual information, you need to identify your animals. You need to understand who the individual is. So here is one of the the models we're developing for individual identification. This is only using the face, but pigs, they can be very similar to each other, so we are also using body recognition. You'll probably have used your phone to unlock, right? And that uses not only a facial recognition of a 2D image, but also uses the shape of your face. And that's what we are developing with body of the animals. Can we use a camera system that can identify the same animal across the entire production system and use that to link back all that information that you have on an individual level? This obviously comes with the challenging on the initial phases of this model. We can see that we're getting very great accuracy of identifying an animal and testing that on the animal up to 4 days after you took that first picture. But pigs, especially when they're this young, they change over time very quickly. So should our models be retrained over time, and how would that happen? That's something that needs to be taken into account. Almost there. Measure what's important, don't make important what you can measure. As I say, as researchers, we are very excited about the cool things, the new things, and what can we do. But sometimes when it comes to implementation, we need to really decide what actually is going to be useful and important. So that there's got to be a balance between we are doing research probably for the next 5-10 years to start being used, but also there are some things that we should be implementing today, and not necessarily you need to measure everything of everything. Each case is a different case. So data is something that's very useful, but at the same time can be very overwhelming depending on how much you're saving. So we are trying to get large amounts of data and actually make sense of that information to provide decisions that need to be taken. And here's an example of big data. This is one image, one pig image, one of those depth images that I showed. It has about almost 400,000 numbers in one image because one image has pixels on it. If I take a video of a pig at 30 images per second, I will have a very large 11 million numbers per second, right, being generated. But in reality, I will not be collecting 1 second of data. I'll collect 24 hours in one day. I have 24 hours of data, but then I will be collecting that every day. So we have almost 1 trillion numbers there. If we want only animal weight, that's one number. Can we actually, instead of saving all of those numbers, can we in real time be analyzing those images and not really being concerned on top of that with privacy issues? Who should have access to those images? Can we develop algorithms that are capable of in real time providing actual information? And to be truthful, a farmer doesn't want to know all weights of all pigs in their farm. They just want to know the one that's not gaining properly, or the handful of the ones that are not gaining properly, and better yet, why they are not gaining and what should be done about it, right? So that's kind of where we are trying to move towards. So then again, the biggest error that technology innovators make is to be seduced by a technology's potential rather than led by the consumer's actual needs. We need to be considering what's needed, both today and in 10 years from now, and develop research that will close those gaps. Finally, a big challenge, but also opportunity, is data integration. It's very complicated to talk with some farmers. They're implementing some of these technologies, and they come to me and say, well, now I have 5 different apps on my phone, and each of them is measuring one different thing, but they don't talk with each other. So data integration is a big thing, and I feel like it's not only about doing research to make those individual components work, but also understanding how those components can be put together, right? This is the final system that we are aiming for, and that not necessarily exists yet. Animal data needs to be transformed into information, and this information then should be transformed into advice, decision, and then action should be taken. One other thing is, if you're providing decisions that need to be taken information in real time, can those actions also be taken in real time? Sometimes you can't do anything about that in real time if you don't have maybe the hardware or to actually implement those things in real time. So what is the frequency of decisions that you should be providing to a farmer so they can actually do something about it? And then outcomes that we are looking for would be obviously the becoming efficient, but also in a worker perspective, we want to have a better work-life balance, right? We need to not consider that our workers, they cannot just be looking at apps and trying to modify the environment all the time. So just summarizing. Precision management of animals or precision livestock farming should provide help for farmers to take care of their animals. Real-time monitoring is very important. We are also concerned about privacy. If we can analyze data in real time, probably better. Farm environment poses some challenges to application of this technology. Should be taking that in consideration. And collaboration is a last point. It obviously is an interdisciplinary area. It's not only one engineer or an animal scientist or a veterinarian that's going to be doing those things. It needs to be a group effort. And just thank you. And I'll take any questions if you have any.
Thank you for that talk. I think it's very interesting to think about the possibilities. We'll open the floor for any questions for Isabella.
Yes.
Can you kind of talk about a little bit of your vision for your behavior work and where you're wanting to take that in the future?
So for the behavior analysis, first thing is develop models that can actually understand behaviors in any phase of the animals. And be very accurate, because the next step would be able to develop time budgets, how much an animal is spending doing this or that. If that model for the behavior is not as accurate as it can be, you're going to be generating behavior time budgets that are wrong. And then obviously any type of decision made after that or any conclusions that you take based on that is wrong. So the first thing is really making sure that we are understanding those behaviors. It's easier to look for individual behaviors when the animals are individually created. When it comes to social interactions, that's probably the next step. We're starting to choose. Obviously, there are more challenges. Just to give an example, for a computer to even understand where's the head and where's the tail of the animal, and that makes a difference if you're looking for fight. You're probably looking head to head or head to the side of the animal. So those things, they seem cool and they seem easy to achieve, but they are not. Once we reach that level of accuracy, that's when we can really make good conclusions about other things and start just providing information for other models to be successful.
Do you see a potential for that work to kind of spill over into the genetic space, so looking at
Yeah.
field selection and things like that?
Yes, absolutely. Yeah. Yeah.
Hello, Isabella.
Hello.
Great talk.
Thank you.
Yeah, kind of leading on from what Grace was saying, I mean, behavioral profiles for duration is one thing, but when you're looking at like the pre-weaning mortality and the maternal index, you may have some other considerations to think through as well. So one would be latency, one would be frequency, and then also how long some of those behavioral postural changes take. So there's been some really nice work between sows and crush and goat by the kinds of lying and rolling patterns, what they consider to be controlled versus not, right? And so there is some, and sometimes it's not just the duration that we're looking for, that actually is the easiest one from a modeling, but there's other nuances with behavioral profiles that you might want to consider, and some subtle behaviors that we're not capturing right now, such as vocalizations change between sow and piglet, horn behavior and things like that. So as you're building this, I think you'll dig into some of these things, but
Yeah.
it's quite complicated. Behavior is really complicated. As much as people think it's simple, it's actually
Oh.
more complicated than
Absolutely, absolutely. I agree.
really like what you're doing. We
Yeah.
can talk further about
Yeah, absolutely. Yeah, I totally agree. We start with the easy ones, obviously, standing, lying, etc. But we are starting to look into time between the postures, if the animal even has those transitional postures, but also things like swinging the head before lying down and things like that. But yeah, it gets very complex very, very quickly.
Time for one more question.
Yes.
For the algorithm developing part for all kinds of work that we published and maintained video, so do we have to develop the algorithm from scratch every time, or is there some kind of transfer learning or something that we can use from the previous work?
It's a little bit of both. It really is developing based on transfer learning from previous research. It kind of depends on how public available people make their models. So if I'm doing a work and building on my own work, I'll just transfer what I learned from one environment to the other. So all my pig detection models, I'm just building on top of each other so I can detect pigs across all phases of production. But it really depends on how public available something is. If a researcher only publishes results and kind of the general view of what the model looked like, there's no way of transferring that specific model. But you can still transfer learn with architectures of models that were developed for human applications, and we use those as well. So it's a little bit of both. We're still not very great at sharing and making both our data and our models public available in this area.